Okay, I'm very excited to be here. Today I will be talking about Thunder, a fast and high throughput cryptocurrency. You can think of this as a very fast version of Ethereum. We are going to support EVM smart contracts. Okay. 2017 is said to be the year of the ICOs, and 2018 the year of the dApps. So there are many exciting dApps. There are games on blockchains. There's sharing economy like Uber and Airbnb on blockchains. There are many others like prediction markets, social networks, and so on and so forth. Okay, so this is all nice, right? There's a lot of excitement. Unfortunately, we also know that today's blockchains are too slow to support the demand of all these dApps. With today's blockchain infrastructure, none of these dApps will actually take off at scale. And let me give you an example. This shows Ethereum transaction fees over time. Now, if you look at December last year, this was an exciting time, partly because CryptoKitties came about in December. And if you compare CryptoKitties with traditional games like social network games or mobile games, it's not like they have a lot of volume, right? In some sense, they have tiny volume. But the single game alone was sufficient to overload the entire Ethereum. And back in December, Ethereum transaction fees were like 1 million USD per day, and they were 90% utilized. So this is how bad it gets. OK, and now I think scalability is the biggest and most exciting challenges our community faces today. And we believe that we have the best technology to overcome this challenge. And even with a single shard, we can achieve more than 100x throughput than today's blockchains, and we can confirm transactions in less than a second. OK. And now, in this talk, I'm going to tell you the secret sauce that enables such a fast cryptocurrency. And the secret lies in the new consensus protocol that we have. It's called Thunderella, and this is joint work with my colleague, Rafael Paz. OK, of course, it takes more than just the consensus protocol to build a fast cryptocurrency, right? You need to have the right incentive mechanisms. You need to have the right governance policy. For today's talk, in the interest of time, I'm only going to focus on the consensus protocol. OK. So now, to understand consensus, the first thing I have to tell you is what problem we are trying to solve. OK, so the problem we are trying to solve here, I will call it state-to-machine replication. It's also called the linearly ordered lock or consensus. And basically, in the rest of the talk, all these terms pretty much mean the same thing. OK, so now remember, we are trying to build a public ledger, right? A public ledger is a linearly ordered lock. In this case, we actually have a traditional scenario. So imagine we have a set of Google Wallet servers. And these servers are also trying to agree on a linearly ordered log of transactions. And there are two important properties that we care about, namely consistency and liveness. Consistency says that all of the honest nodes should agree on the log. But the network, of course, has delay. So it is possible that your log will progress a little faster than mine. And that's perfectly OK. But at the end of the day, we should nonetheless agree on the prefix of the log. OK, the second property is called liveness. Liveness says that whenever a client submits a transaction to the system, very quickly, this transaction is going to appear in every honest node's log. It's not like we want to wait forever for our coffee. OK. So at first sight, this seems like a very boring problem. What is so exciting about building a distributed linearly ordered log? Indeed, if all the servers were honest and they correctly followed the protocol, the problem would have been trivial. But what makes it really challenging and non-trivial is when a subset of these servers can be compromised. Like they can, for instance, have malware, and these compromised or corrupt servers can deviate arbitrarily from the protocol. And even under such adversarial settings, we would like to guarantee that the remaining set of honest servers should still satisfy these security properties. OK. So this is the problem we are trying to solve in the rest of the talk. And the first thing I want to tell you is that actually state-to-machine replication is not a new problem. It is a very old problem. It has been around for 30 years. And the entire distributed systems community have been doing research and development for the past 30 years. You look at all the Silicon Valley companies here, right? And actually, every company deploys state-to-machine replication to replicate their computing infrastructure. And an example is Apache Zookeeper. This is an open source implementation of a Paxos, a variant of Paxos, which is like a crash fault tolerant version of state-to-machine replication. OK, so traditionally, whenever we talk about consensus, the kind of scenario we have in mind is exactly what I talked about. Right? There's a single company like Google or Facebook. There's, roughly speaking, a dozen nodes. And then these nodes are interconnected with fast local area network. So this is like small-scale deployment. And like I said, consensus itself is not a new idea. But what is new here is the large scale. With cryptocurrencies, we are looking at thousands to millions of nodes over the internet. And at this scale, actually, consensus becomes a much, much more challenging problem. And this perhaps explains why all these ICOs and companies out there, everyone's inventing and rolling their own consensus protocol. But at the end of the day, this doesn't make too much sense, right? Because when we took our undergrad security class, we learned that you shouldn't be rolling your own crypto. But consensus actually is just as tricky and as subtle as crypto. So why is it that everyone feel the need to roll their own consensus implementation? OK, so now, in the rest of the talk, I'm going to try to tell you these two things. Number one, like I said, why, after 30 years of work in this space, there still isn't a dream protocol for large scale? Why is everyone rolling their own implementation? And number two, I want to tell you what I'm excited about, what I think is the dream large-scale consensus protocol. OK, now let's start with question number one. Why, after 30 years of work, there still isn't a dream protocol for large scale? To understand this question, it helps to look at the consensus landscape. So what have we done about consensus? At a very high level, there are, broadly speaking, two classes of approaches towards consensus, and I'm going to call them the classical approach and the blockchain-style approach. So for classical protocols we are familiar with, like PBFT, Paxos, and many other variants, they're all classical style. And these are the protocols that Google and Facebook deploy. OK, what do we know about classical consensus? First, when the network has abundant bandwidth, these protocols are very fast. Because normally, you can confirm transactions in constant number of round trips, which is very nice. On the other hand, these protocols are notorious for being incredibly complex, which makes it difficult to implement, difficult for operational maintenance, and also for security auditing. And classical protocols also, we know that they typically don't scale very well to a large number of nodes. OK, so now the more attractive, more exciting approach, of course, is blockchain-style consensus. And the first blockchain-style consensus, of course, is Nakamoto's protocol, right? This is the protocol that underlies Bitcoin. OK, what do we know about blockchain-style consensus? The first thing I want to tell you is that blockchains, they're not just an empirical breakthrough. They're actually, in some sense, a mathematical breakthrough as well. Because now we actually understand the mathematics behind blockchain-style consensus, and we realize that the mathematics there departs completely from classical. So this is kind of like a very interesting point. For blockchain-style consensus, there are two compelling advantages. Number one, the protocol is really simple, right? All you need to do is to take the longest chain and try to mine the next block to extend the longest chain. So very easy to implement. These protocols are very robust. Like we know Bitcoin has been up and running for the past 10, 11 years. So the robustness, in some sense, has been empirically proven. Unfortunately, blockchain-style consensus is very slow, right? So for Bitcoin, we know it takes 10 minutes per block. And if you want to have sufficient confidence, one block is not enough. You have to wait for like 6 to 10 blocks. And that means like you have to wait for an hour for your coffee. OK. Another concern you may have is that these blockchain-style consensus protocols, they are very wasteful because they have to solve expensive proof-of-work puzzles. And Bitcoin consumes maybe more electricity than the entire Iceland. And this is just to confirm 7 transactions per second. OK, for the purpose of this talk, I'm going to ask you to take a leap of faith and assume that this energy waste problem has already been solved. And indeed, in some of our earlier works, we show how to replace proof-of-work assumptions with proof-of-stake and still be able to emulate the mathematics behind Nakamoto. So in the rest of the talk, whenever I mention blockchain-style consensus, I mean both proof-of-work and non-proof-of-work approaches. And you can pick whichever you like. Like if you don't like proof-of-work, you can pretend this is like a proof-of-stake blockchain. Now, even though we can overcome this proof-of-work problem, blockchain-style consensus is still slow, right? So we haven't solved the slowness problem yet. So now, if you look at the landscape, obviously, the question you want to ask is, what is the dream protocol for large scale? Neither these existing approaches are ideal. So I will try to answer this question in the rest of the talk. And the plan is the following. I will start by explaining how classical consensus works. And then in the middle, I'm going to get stuck. And when I get stuck, I will try to combine the best of both worlds. OK. So let's start. OK, this is the scenario we are going to be working with today. We have in the middle, Vitalik, who is going to be a leader. And we also have a committee of voters, right? In this case, the committee consists of superheroes. In a real-world cryptocurrency system, imagine the leader and the committee are elected using some algorithm, for instance, based on stake distribution. Now, some of these voters can be corrupt. So in this example, Loki is corrupt. And of course, the leader can be corrupt as well. So these corrupt nodes keep in mind that they don't have to follow the honest protocol. So what I'm going to do now is to tell you an extremely simple voting-based protocol. And I want us to think together what this protocol can achieve and what it cannot achieve. OK, so here's the very simple protocol, I promise. Number 1, the leader is going to make a proposal to everyone. The proposal consists of a sequence number and a batch of transactions. OK, so the sequence number is going to determine where in the linearly ordered log this batch of transactions will land. Remember, we are building a linearly ordered log in the end. OK, so for simplicity, in practice, you always want to confirm a batch at a time. But in the rest of my talk, I'm going to call this a transaction instead of a batch. And also, like remember your entire protocol for building this linearly ordered log is going to consist of many little instances of this little protocol. But for the time being, we are going to focus on a single instance with a single sequence number. OK, so step number 1, the proposal. Step number 2, everyone's going to vote. And the vote is simply a signature on the leader's proposal. OK, in this example, the leader proposed a golden transaction to everyone. Now, if you are honest, you are going to vote on the leader's proposal. So you would be casting a golden vote. But remember that Loki is corrupt, so he doesn't have to follow the protocol, right? So in this example, he didn't cast a golden vote. Instead, he casts a red vote, voting for the red transaction. And also, he voted for the blue transaction. OK, so now what do? We wait. we wait until we hear enough votes on the same transaction. So if enough people vote for the same transaction, then we have enough confidence on the transaction, and we think it's like, safe to confirm and output it. OK. So very simple protocol, right? Very natural. And the most important thing to notice about the protocol is that the honest nodes are going to vote uniquely. So this is a very important invariant. If I'm honest, what I'm going to do is I will wait until I hear the first proposal from the leader, and then I will vote on that proposal and only that proposal. I'm not going to vote on anything else. OK, so this is going to be important for proving consistency, and that's what I'm going to do right now. I want to show you why the protocol satisfies consistency, and it turns out the proof is actually extremely simple. OK, but to prove consistency, I have to first specify some of the parameters I'm assuming. Imagine in total there are n voters, among which less than 1/3 are corrupt. OK. And then in this case, I claim you only have to wait for 2/3 of the committee to vote in order to confirm. And that's enough to get consistency. And why? So let's look at this very simple proof. In this example, Spider-Man has heard 2/3 people voting for the red transaction, and Iron Man has heard 2/3 people voting for the orange. What I want to prove here is that the red transaction is the same as the orange. And how do I prove this? I'm going to look at the red set and the orange set, and I claim that there is at least one honest node in the intersection of these two sets. And this follows very simply from pigeonhole principle, because remember that there aren't too many corrupt nodes. OK. So now, if you believe this, then you can look at that honest node in the intersection. And remember what I said about honest nodes, right? They're going to vote uniquely. And because that honest guy in the intersection voted uniquely, we have that the red transaction is equal to the orange. So very simple consistency proof. And notice that in this consistency proof, I never relied on the leader being honest. The only thing I'm relying on is that the honest nodes vote uniquely. OK, so with this in mind, let's kind of think about the bigger picture. What does this protocol give us? So on the left-hand side, we have the world when the leader is honest. When the leader is honest, everything's good. We have both consistency and liveness. Consistency, I've just proven to you. So why do we have liveness? If the leader's honest, he's going to make the same proposal to everyone. And because there are at least 2/3 honest nodes, and they're going to vote consistently based on the leader's proposal, and very quickly, this proposed transaction will gain enough votes, and it will get confirmed. OK, so what about the case when the leader is dishonest? In this case, we actually still have consistency, because remember the proof I've just presented to you, the consistency proof never relied on the leader being honest. OK, but unfortunately, in this case, we don't have liveness. And why do we not have liveness? If the leader is corrupt, for instance, he can just simply crash and not make any proposals. In this case, no one will cast any votes. And of course, the protocol will get stuck. But he can also propose different things to different people, so everyone ends up voting on a different thing. And in this case, nothing will gain enough votes too. OK. So this is what we have with this extremely simple protocol. It seems like we are almost there, right, except for solving this liveness problem. So there is just this one little problem left. So how do we solve this one little problem that's left? If you look at all these classical approaches, they resort to a very complicated recovery mechanism to re-elect the leader and to retry. And then I don't want to have to explain how these classical approaches deal with this problem. But I do want to mention, right, that there are many of these variants of the classical approach, but pretty much they follow the same structure. If you look at all these protocols, there's a very simple normal path, which consists of one or more rounds of the voting kind of protocol I talked about. But then when the normal path fails, these protocols would resort to a very complicated recovery path. And when you look at the picture, right, operationally, you want that almost all the time, the system operates in the green area. Like you always want to be on the normal path. But when you look at the code base, most of the code is actually in the recovery path. And that's where all the complexity and bugs are. And this complexity actually has practical implications, like Chain.com is a San Francisco-based company. They're rolling blockchain solutions for Visa. And they basically chose to implement only the normal path. Like they don't want to implement this complicated recovery path. But what this means is that suppose their normal path fails, then they have to do all this complicated stuff manually. And imagine if this protocol is deployed among 100 banks and 1,000 nodes. You now have to like sync up all the locks among these 1,000 nodes, and you have to like rebootstrap the protocol manually. So this is going to be a huge pain. Okay, so at this point, we are kind of stuck. And as I promised, now it's the time to try to combine the best of both worlds to get the dream protocol. Okay, and our idea is the following. It's actually very simple. Let's get rid of all this messy, complicated stuff and replace it with the extremely simple blockchain. So this is the high-level idea behind Thunderella. I mean, of course, simple as it may seem, it's actually a little bit subtle to instantiate this idea correctly. So I'm going to tell you how to do this. And the terminology I'm going to use is the fast path and the slow chain. So the slow chain can be any standard blockchain like Ethereum, like Bitcoin. But if you don't like proof of work, it can also be a proof of stake blockchain. OK. So the goal we're trying to achieve here is that we want that almost all the time, the protocol should be operating in the fast path. And in the fast path, we want transactions to be confirmed in 2 to 3 actual network round trips without having to wait for even a single block interval of the underlying slow chain. And moreover, if you are in the fast path, you shouldn't have to post many messages to the slow chain. Right? You only have to post tiny messages to the slow chain, and almost everything just gets confirmed on the fast path. So now, even when things are not so good, so let's say we are under attack, it's not the end of the world, because we always have the slow chain to fall back to. So even in the worst case, we are getting the security and performance of today's slow chain. But almost all the time, we should actually be operating in the fast path. So this is what we want to achieve. And just to quickly recall the scenario, we have a leader, we have a committee, and now we also have a slow chain underneath, right? So the slow chain, as I said, it can be Ethereum, it can be Bitcoin, it can be a proof of stake slow chain. There's going to be some mechanism for electing the leader and committee, like for instance, based on stake. And the leader and committee can rotate over time. But for the time being, I'm going to assume that this election has been done, and we are going to work with this single snapshot. So to get the worst case robustness and security, we need to make some assumptions. And in particular, we will assume the underlying blockchain, the slow chain, is secure. And typically, this means we have to assume honest majority. If this is proof of work, honest majority in compute power. If it's proof of stake, honest majority in stake. We will also assume the committee is majority honest as well. Okay, we don't have to assume anything about the leader. So under these conditions, our protocol gives consistency and liveness. Okay. So I'm going to tell you the protocol now. I will start with the fast path. And in fact, I've already kind of told you how the fast path works at the very beginning, but I'm just going to quickly revisit it. And what I want you to pay attention to now is what happens when there are multiple sequence numbers. Like earlier, I focused on only a single sequence number. OK, so remember, the leader makes proposal, the committee will vote. When a transaction gains votes from 3/4 of the committee, I'm going to call it notarized. OK, so earlier the threshold was 2/3. Now it's 3/4. And the reason is now we are assuming minority corrupt. Earlier, we only wanted to deal with 1/3 corrupt. So if there are more nodes corrupt, the threshold needs to be higher to get consistency. OK, So in this example, transactions 1, 2, 3 have been notarized, 4 is missing, and 5 and 6 have been notarized too. In a cryptocurrency system, it is important that you process the transactions in a linear order. Like for instance, 4 can be trying to double spend the same coin as 5, and unless you process it in a linear order, you wouldn't be able to catch that. So in this example, the only prefix we can process is up to 3, right? So for the lack of a better term, I'm going to call this the maximal lucky sequence. The maximal lucky sequence is what you can confirm and output. OK, so if the leader is honest, then everything would be good. The lock would keep developing over time. And remember, the problem we have always been trying to address in the talk is what happens when the leader is dishonest. How do we get liveness? So now let's get to the real problem. So far, we haven't used the slowchain yet. And of course, we have to use the slowchain somehow. So I'm going to try to use the slowchain to answer this question. We are going to use the slowchain for 2 purposes. First, to detect when the fast path fails. And when we detect that the fast path has failed, we will use the slowchain to do a fallback. Nodes can continue to confirm transactions on the slowchain even when the fast path fails. But when you are in the slow mode, you don't want to be stuck there forever. You should always try to re-bootstrap the fast path. OK, so I only have to tell you about 2 things. One is how to do this detection, and the other is how to do the fallback into the slow mode. And let's start with number 1, how to do the detection. Now, the challenge here is that we need a robust mechanism. We need a detection mechanism such that faulty nodes cannot falsely implicate an honest leader. If they could, then they could launch a denial of service attack, which would be rather bad. OK, so what should we do here? Here's a very simple idea. Let's imagine normally, when we are on the fast path, every now and then, the committee is going to take a hash of the fast path lock, and they're going to sign the hash. When this hash gains enough signatures, it becomes notarized, and then the accelerator and committee will post this notarized hash to the slow chain. And this is going to be called a heartbeat. A heartbeat is a notarized hash of the current fast path lock. So it can also serve as a checkpoint, right? Because this hash cryptographically binds to the fast path lock. What I want to stress here is that notice during normal operations on the fast path, the only thing that we post to the slow chain are the heartbeats themselves. And these heartbeats are tiny. So that's why we are not subject to the throughput of the slow chain. Like our fast path has much higher bandwidth, and that's why we have a much higher throughput. OK, now, when things are good, the heartbeats should keep beating. Suppose at some point I notice something weird. Say, k blocks have gone by without seeing any heartbeat. So k is a security parameter. For Ethereum, you can imagine k is 300. Now something weird is going on, right? What can be causing this? Imagine if the leader is corrupt. For instance, he has crashed and he stopped making proposals, then no one would be signing anything. In this case, the heartbeats will stop. Or maybe if the leader is corrupt and he's trying to censor transactions, and the committee have noticed that and they're trying to rat the leader out by refusing to sign, in this case, the heartbeats would also stop. In either case, the fast path has broken, and we want to fall back to the slow chain. So how do we do this fallback? It may seem like this should be an easy idea to implement, but there's also subtlety here. And the challenge is the following, right? So suppose at this moment, Spider-Man, Iron Man, they both want to fall back, but the network has propagation delay. So in this case, Spider-Man's network is a little slower. So when he wants to fall back, he thinks the fast path lock ends at 3, but Iron Man thinks the fast path lock ends at 6. And these 2 guys have to reach agreement on where the fast path lock ends before falling back to the slow chain. And this is the nature of the problem here. OK. So when you think about it a little bit more, you realize this actually is an agreement problem in itself. And unlike earlier, when I talked about the simple voting-based protocol, I punted on liveness. Here, we have to solve the problem in full. We have to have both agreement, consistency, and liveness. So it's actually, in some sense, it's actually a non-trivial problem. Fortunately, again, we can use the slowchain for help. The way to think about it is like the slowchain, although it is slow, it is a sure and steady consensus mechanism that is always there, even when the fast path fails. So when the fast path fails, people can use the slowchain as a decentralized public bulletin board to communicate with each other and to discuss, how to fall back and how to rebootstrap the fast path. Okay, so now, how do we do the fallback? We will introduce what is called a grace period, essentially these green blocks. And there are k of these green blocks, where k is a security parameter. For Ethereum, think of k as 300. Okay, now, what happens when I want to fall back? The first thing I do is I stop signing on the fast path. And I will also tell everyone else what I have seen, like all the notarized transactions I have seen on the fast path. Okay, now, I also need to post all the notarized but uncheckpointed transactions to the slow chain, into the screen part. So remember, the heartbeats also serve as a checkpoint. And if the transaction is already vouched for by a heartbeat, it is considered as checkpointed. And I don't have to post these checkpointed transactions to the slow chain. I only have to post notarized but uncheckpointed. So this goes on. And at the end of the grace period, the nodes would have reached agreement on where the fast path log ends. So very nice. There is actually one more subtlety here, in the sense that if at the beginning of the grace period, right, in this case, Spider-Man thinks the fast path log ends at 3, so he believes the first 3 transactions have been confirmed, it is important that the log doesn't roll back at the end of the grace period, because these confirmed transactions should not be undone. So what we can guarantee is that at the end of the grace period, the maximal lucky sequence contained up till the end of the green blocks is at least as long as where everyone started at the beginning of the grace period. So no one's log will ever roll back. Okay. So that's basically how we resolve the liveness issue. To summarize, we use the slow chain to detect fast path failure, and then we use the slow chain also to fall back. But of course, when you are in the slow mode, you should always try to be optimistic and rebootstrap the fast path again. Okay, let me just quickly revisit the guarantees we can provide. If you want worst-case security and robustness, you only have to assume honest majority. I want to stress at this point that the leader need not be trusted. So what can a malicious leader do? Even if the leader is arbitrarily malicious, the only thing it can do is to slow down the protocol, right? Because the leader can always just crash, and then the fast path would shut down. However, the leader cannot break consistency, and it cannot stop the system either, no matter how it behaves. And this is very important because that's why our system is fundamentally decentralized. In other words, the leader actually is more like an accelerator. Much as Akamai is the accelerator of the internet, the leader here is kind of like an accelerator of blockchains. Okay. And also, this is also why our system can kind of achieve the best of both worlds. We have the security and robustness of decentralization, but we actually have the performance of centralization. Okay. Okay, so when things are good, we can confirm transactions very fast and with high throughput on the fast path. And what does it take to stay on the fast path? We need to have that the leader is honest and online, and 3/4 of the committee honest and online as well. So this is a stronger set of conditions than the worst case security, the conditions required by worst case security. But of course, what I pointed on in the whole talk is like we actually have incentive mechanisms to make sure it is actually in the leader and the committee's interest to keep the fast path up and alive so they can earn rewards and transaction fees. Okay. So that's kind of the protocol. If you want something to remember by, here are the 2 sentences you should remember. When things are good, the protocol uses a single round of voting to confirm transactions on the fast path. And when things go bad, we use the slow chain to do fallback. So when you are in the slow mode, you should always try to bootstrap the fast path. OK, so now with these 2 sentences, you should be able to reconstruct the protocol yourself at home. OK, very simple. I omitted many details, like I didn't discuss how to do leader committee election. Our implementation has practical optimizations, which I didn't have time to cover. In our paper, we also have mathematical proofs of security. Before I conclude, I want to tell you some of the deeper insights we gained. In particular, why, after 30 years of work in this space, we can claim to be simpler and yet faster than everyone else. OK. If you look at all these classical consensus protocols, they work in what's called the asynchronous model. So what are asynchronous protocols? An asynchronous protocol is unaware of the maximum network delay. The protocol does not know how long it takes to deliver messages. In other words, any asynchronous protocol is a universal protocol that must work for any network delay. And because of this requirement, it is very challenging to design these protocols. So these protocols are typically more complicated. If you look at Thunderella, we actually kind of baited and switched because we are using a synchronous protocol underneath. And this is also saying blockchains are synchronous. And why is this the case? Because we know that the block interval has to be like 60 times larger than the maximum network delay to resist 49% attack. So this means that whenever I parameterize the block interval, I have to be aware of the maximum network delay. And that's why blockchain protocols are synchronous. OK. So the interesting thing is, in this classical body of work in distributed systems, the synchronous model is, in some sense, almost completely neglected by the community. And because the classical wisdom is that synchronous protocols are slow, right? If you think, you are Google and Facebook, you want microsecond to millisecond latency. And in this case, you don't want to even wait for a single block interval or a single synchronization round. Because this block interval or synchronization round has to be set very conservatively. Like if your average network delay is 1 second, you might want to set the parameter to 10 seconds. Because if this assumption is ever violated, all bets are off. OK. So you simply cannot just afford to wait for a single synchronization round. But our insight is that this classical wisdom is not exactly right. Because if you look at Thunderella, very interestingly, almost all the time, we operate in asynchronous land. But then if you look at the protocol, it is fundamentally a synchronous protocol, because it fallbacks to a synchronous slow chain. Right? So this is how we actually get the best of both worlds. OK. So this actually turns out to be a new theoretical paradigm. Like with this new paradigm, you can get interesting theoretical results as well. Like here's one of them. There are many others. So classically, if you want your protocol to be fast, we typically believe that the protocol needs to be asynchronous. But there is a lower bound for asynchronous protocols. That is, these protocols can tolerate only 1/3 corruption. And this is actually a very well-known lower bound. Now, this seems to say, like, if I want my protocol to be fast, I cannot tolerate more than 1/3 corruption. But our insight is also, this is not necessarily true, because if you look at Thunderella, we are fast almost all the time, but we overcome this barrier. We can tolerate minority corruption. OK. So finally, I wanted to say that what I like best about this protocol is that it's extremely simple. And in a large-scale distributed system, simplicity is going to be our best friend. And our company is actually in Sunnyvale downtown. We are hiring, and we have many types of positions open. We also would like to partner with dApp developers. So please contact us. And also, I wanted to say that our testnet is coming out in the next few days. So just pay attention to our testnet launch. And if you want to try it out, please contact us as well. Thank you.